Okay, so let's solve this equation for the case of this delta function potential. U naught delta of x times w is minus lambda w. Okay, so for a start off, so we've got lambda is less than 0 and lambda is equal to minus k squared. So we know immediately that w must be given by these two exponentials. And we can only have it's got to be bounded, so it can't grow. So we have the positive root when x is less than 0 and the negative root when x is greater than 0. So we're going to try and now we've just got to work out what these coefficients a and b are. And we know, just looking at this equation, we know that if a was 0 and b was 0, then w would be 0 and it would satisfy this equation. So we're going to end up with a typical eigenvalue problem where we have to work out what value of k, which is in turn what value of lambda, will allow a solution that's non-trivial. Okay, so what happens at the join? So what we do is we integrate across the jump from 0 minus to 0 plus the x derivative squared of w. It's like finding a Green's function. It's u naught delta of x of w plus lambda w dx. We know that's going to be 0 because it satisfies that equation. And then we're going to get, when we integrate this, we get the x derivative of w at 0 plus minus the x derivative of w at 0 minus. Okay? The integral of the second derivative is the derivative from the value at the endpoints. It's not going to be continuous, this function on the jump. Plus, we get u naught times w of 0 equals 0. So that's the condition, that's the jump condition, the jump in the derivative. And we also get that the w of 0 minus must equal w of 0 plus must be, so it's continuous. W is continuous. So if we combine those two conditions, we're going to get a condition on A and B, aren't we? So the first equation was going to become, what's going to happen here? The x derivative is going to be plus is going to be minus b, right, multiplied by k. And then the minus 1 is going to be a minus from here, ak. So plus uw of 0, which is u times a, if you like, must u naught times a, okay, equals 0. Or whatever w of 0 is, because the w of 0, the other condition is that a must equal b. Right, so w of 0 plus and w of 0 minus are both equal, and so a must equal b. So it doesn't matter if you take u naught of a or u naught of b here. Okay, so that's the system of equations. So we've obviously got the solution a equals b equals 0, so we need to find out when would we be able to get a non-trivial solution. So we need something special to happen with the k, and you can see here that we've got to have, this equation has to have a non-trivial solution when b is equal to a. So we've got minus 2b times k, right, must be equal to minus u naught b, okay, assuming that they're replacing a with b. Alright, so therefore you've got to have, only in the case when minus 2k naught is equal to u naught minus u naught, do we have a solution, do we have a non-trivial solution. Okay, for that us to have a non-trivial solution. So we need and effectively that's looking for some determinant of this matrix must be equal to, not equal to 0. Because if we write that as a matrix equation, it's one minus 1, and it's, if we write this as a matrix, you've got minus b times minus b, minus k, sorry, over here, and here you've got minus k plus u naught. Okay, so we need the determinant of that matrix to be equal to 0. All right, which happens when k is equal to u naught over 2. Okay, so we've solved that equation, and we've found what this, we've solved the solution for when lambda is less than 0. We find a single, eigenvalue. So if your lambda is less than 0, is a single eigenvalue on a single eigenfunction, okay, given by k is equal to u naught over 2, and lambda is minus k squared. And the solution is given by w equals a e to the kx. Okay, and I'll just follow the notation in the notes. I think I call it k1 for some reason. Not sure why. So I guess because there's only one k, sometimes you're going to get 2 k's. And you call the second one k2. Great work. Okay, k1 is u naught over 2. And finally, we can normalize. It's not super important to do this, but we can normalize w, and we want to have the integral from minus infinity to infinity of mod w squared. So that's the L2, length is equal to 1. So that means that it's symmetric, right? So we'll just go from 0 to infinity. Whoops, I'm trying to, here, I put b here, but obviously it's a. Okay, because we know b is equal to a. Okay, make it purple. Well, that's going to be a. Oops. Wrote b again for some reason. There, that's a. So we want, just take this one, half of it, if it's symmetric. So 0 to infinity, the modulus of a e to the minus k1x squared dx. This has to be equal to a half. So if we integrate that, we get a squared e to the minus 2 k1x over minus 2k1 from 0 to infinity is equal to a half. And this is going to be equal to, alright, I'll write up here. So you're going to get k1, infinity becomes 0, 0 becomes a squared over minus 2k. So we get a squared over minus 2k1 is a half. So a must be equal to the square root of k1. Okay, so we can get up here. I'm going to, rather than writing in that corner or rubbing it out, I'll rub it out here and I'll put it in. So that's the final step is to normalize. Eigenfunctions are always defined up to a constant by definition. So this is the square root of k1. All right. So you get this decaying exponential function, right? That and as the k becomes bigger, it decays faster. It's more trapped, but there's only a single value that you get. So that's the solution for lambda is less than 0. And now we're going to go and solve for the case when lambda is greater than 0.